Continuing on, we've basically built the infrastructure that we're going to use to investigate several items here. So just as a reminder here, and I'll close that out, we have persons, and the persons are embedded in populations, and in this population, and persons are exhibiting this this shifting between different compartments, and we noted that there's a fair degree of variability according to parameters. So with baseline, for example, we have a situation where there's a short enough duration of infectiousness and a long enough duration of immunity that while there's some initial spread infection, the infection and sort of some cycling associated with this, after a number of rounds of this, what's going to happen is that the infection will die out of the population. In order to see this more graphically, I'd like to add in a graph that shows the number of the fraction of people infected over time here. And to do that, we're going to put in place a statistic that will compute the prevalence. We saw this yesterday. How are we going to do that? How are we going to have a statistic that will compute prevalence? How would we put in place a statistic to compute prevalence? Yeah. Spoon and yogurt. Yeah. Thanks. How would we put in place something to compute the prevalence at the current time? Yeah. Yeah. Exactly. Let's make it fractional prevalence, just so we rehearse that. This is kind of muscle building stuff. So we're going to call this fractional prevalence. And how are we going to do a fractional prevalence? Anyone remember? Thanks. The average, yeah, exactly, of 0 and 1, you got it. Yeah.
It feels a little warm in here. I don't know if other people feel like the room is warm.
Okay, so could you press the night vent over there? We need to frob the night vent periodically. Thank you very much. Yeah. Yeah, you hold it in. You push it and you hold it in, okay, is my understanding. Okay. Yeah. Thank you for letting me know. We'll try to make sure the doors are fully open too, okay? Okay, fractional prevalence. So thing over which we're taking the fractional prevalence, I like to put in parentheses just so it's clear. So what are we going to ask here? We're going to ask, is the person in state person.active? If so, we count them as what? 1.0, otherwise it's 0.0. So it's going to be adding up value of 1 for each person in the population who's infective and dividing it by the number of people in the population. Why? Because that's what average does. It totals things up and divides by the number. So this is going to compute the fractional prevalence. And we heard an explanation from me yesterday. I don't want to elaborate in the interest of time. So we have fractional prevalence, okay?
Why is it item dot there and not like person dot?
Because for statistics, it goes through each person in the population in turn and calls them item. That's how statistics work, and it will remind you of that with this little bulb, light bulb. Do you see it? Each person, call them item, and determines if this is true, determines their value, since we're doing an average of it. If it were a count, it would be determining is it true or not. Here it's an average, so it determines the value for each person. So the person is effective, it's 1, otherwise 0, it goes on to the next person, calls them item, and determines that for them, taking the average across the population for them. Okay, so that's a great start. Now, ladies and gentlemen, I would like to go and we're going to put in place a data set that depends on that. Okay? A data set. Okay, so where does the data set live in AnyLogic? Can anyone say? Sorry? It actually lives, though, in the palette where? In the analysis tab. So we need to drag into the model from the Analysis tab data set. And this is going to be called Fractional Prevalence Data Set. Okay? And I'm going to use it to show another feature of graphs, but I'm also going to use it with the parameter variation experiment. So it's called Fractional Prevalence Data Set. Is that okay? Data set. Sorry, not data. Data set. And we're going to use time as the horizontal value. Guess what the vertical value will be? Remember, data set consists of x and y values. What will the y value be? The x value is going to be time. What will the y value be? Fractional prevalence. How do we get that? How do we get the fractional prevalence at the current time? Okay, this dot population dot, yeah, fractional prevalence. By the way, I feel a cool wind a-blowing.
It's working.
Seems to be. Seems to be. Do you feel that? Okay. I think it's coming out of this thing here. Okay. Okay. So we can build the model. Okay. Great. And now we're going to go up and do one more thing. We are going to add in also from the analysis palette, a time plot. And that time plot is going to plot out the fractional prevalence. So it will be called fractional prevalence time plot. Now, in fact, plots can show several things on them simultaneously. Fractional prevalence time plot. What is the data going to be in here? Well, we could just make a call. You notice you have an option here. You can either have it use a value, in which case we have it use the value. I'm sorry. I dragged the wrong thing. I dragged in a plot. What I actually wanted to drag in was a time plot. So I'm going to get rid of this, and I'm going to drag in a time plot. Please forgive my mistake there. So this is delete. Boom. Boom. And then here we're going to drag in time plot. Okay? Time plot is what we want. Not a regular plot. Okay. A regular plot would be a scatter plot, which is also of great interest. In fact, we may come back to that. So it's a time plot, fractional prevalence time plot. The data here could be a value. We could just, one thing we could do, let's call it a data set. Title, ooh, it's an unhappy camper. Occasionally AnyLogic does that. This would be fractional prevalence. And the value for it could just be, to be clear, I could just say population.fractional prevalence, okay? But I actually have already a data set that does it. So I'm going to say data set, and I'm going to say this.dataset fractional prevalence. There are times it's useful for other reasons to just do it, just do it with a data set. And so I'd like to be able to show you that. So fractional prevalence data set. Sometimes you can build up data sets in more sophisticated ways. And it's nice to be able to display them on the graph. And this kind of gives an indication about how you do that. Okay? Okay. Great. Ladies and gentlemen, so let's run it. Oh, yeah, well, okay. We'll use it to teach a life lesson. Great. We're going to run this now, and we're going to see it exhibit some dysfunction. So here we go to baseline. There we go. Let's go up above, and we will see it. Here's the fractional prevalence. Do you see that, ladies and gentlemen? Do you see it? Look at that. It exhibits fluctuations. But look at what's happening. It's starting to really scroll fast for my liking. This is in days after all, and it's not even viewing one full year. Note the interesting oscillations, and it's a bit too confined for seeing the big pattern. And then look, what happened, ladies and gentlemen? What happened? Sorry? Okay, so how are we going to fix that? Anyone? Well, first of all, we need to be aware. Maybe it's the data set that's losing the data versus the graph. But let's have the graph at least display several years worth of data. I'm going to ask it to display 1,000 samples here, okay? And the time window here is going to be 1,000 as well, model time units. Note that I could say explicitly a time unit as well, but I'm going to say 1,000. So this is in the data set, or sorry, this is in the plot, the time plot. Are we okay with that? Ladies and gentlemen, are you okay with that? That was in the time plot. We said display up to 1,000 samples, time window of 1,000. Why are they the same? Well, remember, it's updating once a day. So I didn't emphasize that, but its update time is based on once per day. You notice it says update data automatically once per day. So I wanted to show sort of a number of samples comparable to its total number. And then for the data set here, I wanted to keep up to 1,000 samples. Actually, I wanted to keep up to 5,000 samples for the data set. That can be broader than what's shown in that graph. Okay? Daily data, I want to save up decades worth of data, 5,000 latest samples. Okay, ladies and gentlemen, so let's go back to the baseline, and we're going to run this thing. We're going to observe the dynamics. Here we go. You notice these dynamics. Characterize them. What features do you note in those dynamics? Well, there's a couple of them. First of all, it exhibits fluctuations that are cyclic in character. There's oscillations. And in system dynamics, we characterize those with stocks and flows. But here, they're occurring in this network. And then at some point, ladies and gentlemen, it dies out. Dies out completely. Why is that? Well, I argued it's a stochastic thing. But at some point, there's someone that the people that are recovering have no one from whom to get infected. Okay, now let's try a period of brief immunity. How does that change things? You notice that the fluctuations are less pronounced. With briefer immunity, people are getting mixed together. You know, people recovering from immunity, becoming susceptible, are often recovering quick enough they're getting exposed to people who are infected. You don't see these pronounced dynamics associated with where the infection goes down to low level and pops up again because just a few people have gotten exposed and everyone else is susceptible, and it shoots up again. Next, ladies and gentlemen, let's look at this long infectious period. Okay? A long infectious period here. Also, you see a lot of sort of smaller fluctuations, but it's nothing like the most pronounced behavior that you saw earlier with the baseline, where we have really big swings, really big oscillations, and then extinction. Okay? This brings a natural question to the fore. How would the dynamics be different if we had a larger population? A population, ladies and gentlemen, not measured as 100, but a population, say, in the thousands. So let's create a copy of baseline. Remember, we often copy scenarios and paste them so we can get easy reuse. Oh, in fact, I stand remiss. Let's go back to baseline and let's go fix this dependence on a random seed. Let's make it a random seed. Sorry, it was depending on a fixed seed. Let's make it a random seed so that every time we run it, it will be different. Now that's a setting we wish to preserve. So if we run this now for the baseline, we will see differences between runs as the exact timing. Sometimes it will go extinct sooner. Sometimes it will take longer to go extinct. I'm going to turn off the virtual mode here so we see the infection spread here. Here we see it spreading, and in this case, ladies and gentlemen, it's actually gone extinct in the very first round. Okay? Great. Okay. So you could see there's quite some randomness. Sometimes it persists, sometimes not. Great. So let's go and make a copy of baseline with a larger population. Why copy baseline? So we inherit those same settings, most notably here, these randomness settings. So we'll say, population 1,000. Okay. Now, we have to be rather careful when we do this, because if we want to compare apples with apples, there's maybe some other parameters we have to adjust to be consistent. For example, here, the length of the connections between people needs to take into account the changed number of people, or we need to spread those people out over a larger area. And it is the latter option that we wish to undertake, ladies and gentlemen. Okay? So we're creating this population size 1,000, but we're going to crush these people into a small area. They're going to be at much higher density unless we also enlarge the area. After all, we've enlarged the population. I was going to say increase it to 10,000, but maybe I'll increase it instead to 1,600, okay? 1,600. So we multiply it by 16 times. So I'm going to put them in a space that's 4 times larger along each axis to preserve the density. Because remember, they're connected together based on distance. And if we just make it 1,600, they'll be wedged into a tiny space, and each person will have tons of connections. We want to preserve the number of connections each person has. And for that reason, if we have 16 times larger population, we want 16 times larger a space. So the density is not so large that each person has tons more connections. So in order to do that, ladies and gentlemen, we're going to go and we're going to set the size of the space. And unfortunately, regrettably, this is something which, and I'm misremembering here, we're going to set it so that in main we have a larger space. You know, notice here the space, width, and height are set. We're going to go add into this model a parameter that is going to be called space width, and by default it's going to be 500, and space height, and by default it's going to be 500 as well. Okay, 500 space height, and it will be 500 by default as well. We will now use that within main as the width and height of that space. Okay, main, the width here will be this dot space width, and the height will be this dot space height in main. So what did we do? We went and we added a parameter called space height and a parameter called space width to main. We made the default value 500, and we went to main and we said use space width, the parameter space width is the width, space height is the height. We want to change it, in short, by different experiments, so that we can, amongst other things, maintain the density desired. Great. This is a bit of a subtle point, but when we're comparing model runs, we want to vary often one thing at a time. We don't want to vary population size at the same time as we're totally varying the density and hence the number of connections people have. And it generally goes to the notion of dimensional analysis and systematic designs of experiments from a dimensional standpoint, which is a rich and fertile area when you apply it to dynamic modeling. Okay, ladies and gentlemen, just about done. For the population of 1,000 now, we want to go down, and for space width, we want to put 500 times 4.0, and for space height, we want to do the same thing. Why? Because we want to increase the space by 16 times, so it's going to be 4 times larger on one axis, 4 times larger on the other. Total of 16 times larger if you consider it in terms of the area. Each side of it is going to be 4 times larger, so the area as a whole is going to be 16 times larger. Okay? Okay. So, having done that, we should be able to run this model with this larger population. This population, ladies and gentlemen, of 16. Oh, notice it says a population of 1,000 in its name, but it's actually 1,600. Let's change the name to accord with the actual value. Population 1,600. And notice once again, it highlights for us the things that are different from the default values. Okay, we're going to run this. Here we go. Okay. And it's nice because we did lay people out between space height and space width. Look at how it's oscillating here, ladies and gentlemen. It's exhibiting oscillations as successive generations of sick people filter through, and now it's kind of reaching a little bit of a stochastic equilibrium where it's fluctuating around some level. And if we were to rerun this again and again, we would see a similar dynamics where it sort of oscillates and then it approaches some equilibrium. Okay, ladies and gentlemen, wish Kurt were here to see that. He'd find that pretty neat too. Okay, good. Okay, so now we're going to take this in a different direction. We've laid all the groundwork, and now, ladies and gentlemen, we are going to say we want to probe how does the behavior of this model differ as we run it many times, because we've been running it one time and we saw there's actually quite a bit of stochastics when we ran the baseline with a population of 100, of merely 100, quite a bit of variation about when it died out. Sometimes it went on for a long period of time, sometimes by happenstance there was no one around to infect the people recovering by waning immunity or losing their immunity by the time that they became susceptible. So, ladies and gentlemen, we're going to add a new type of experiment here. New experiment, and this experiment will be a parameter variation experiment. And we're going to copy, and it says time settings. We're not paying much attention to time here. We're going to finish it. Okay? Now, parameter variation experiment we'll want it, in this case, to finish within a certain defined time. And so we'll want this to run from time 0, this is for the parameter variation experiment, to time 1,000. And we're going to use parameter variations experiments for two things here, ladies and gentlemen. Item 1, we're going to use it to probe the effects of stochastics. Item 2, we're going to use it to probe the impacts of parameters as they vary. So, item 1 here. Here we go. We're going to have it stop at time 1,000. Note for the parameter variation, I set it to stop at time 1,000. Now, that's just the start. We're going to need to add some items into this parameter variation experiment so that we can see some results that are clear. So, from the palette, go to the parameter variation experiment, and I would like you to drag in from the palette, ladies and gentlemen, a couple things. One thing will be a histogram. Actually, we're going to do it in the same order we did last time. Histogram 2D data. So last time we dragged in a histogram. This time it will be a 2D histogram. It will be a histogram that is binned, divided into bins along both the x-axis, which corresponds to time, and the y-axis, which corresponds to values. Okay? So we're going to call this fractional prevalence histogram 2D. Secondly, we're going to drag in a histogram 2D data object. Histogram 2D data, we're going to call it. And, okay, actually, we'll call it fractional prevalence. Fractional prevalence histogram 2D data. So now we have a fractional prevalence histogram 2D and a fractional prevalence histogram 2D data from which it will draw its values. Okay. Now, like for a histogram, it depends on data to show. How will I show it? How will I show this data? Anyone? Well, we need to say data here, and we need to add histogram data. And guess what? To what we'll be pointing it here? Anyone guess? We'll point it to this dot fractional prevalence histogram 2D data. Boom. That's to what we point it, okay? And this will be called fractional prevalence. Fractional prevalence. There we go. Kurt and Iden, are things good on the food front?
Yeah, it'll be ready at noon.
Okay.
So we'll go down and pick it up then. And then
Grateful.
it'll be ready here.
That's great. Yeah, you won't have to balance it on your motorcycle.
No. I
Okay.
can just make 7 trips.
Yeah. Okay. Good to hear. Okay, ladies and gentlemen. Okay. Okay, ladies and gentlemen. This fractional histogram 2D, you notice that this allows you to set a lot of specifics. And we're going to change the x-axis values to be much more numerous. Remember, it goes to size to 1,000. So we're going to set the number of intervals here to be 250. So each of them will represent 4 units, 4 days of time. And on the y-axis, we're going to set it to be 100 intervals. So it's going to divide up the fractional prevalence into 100 bins, where on a given set of 4 days, it's going to be asking, where did the fractional prevalence lie, and put it into the appropriate bin on the y-axis. Okay? Are we okay with this? Okay. Now, we will further say here, do not update automatically for the data update. Okay? Do not update data automatically. Okay. Now, fortunately, we are almost done now with our little parameter variation setup. But there's one thing, a thing that many of you will consider ugly that we have yet to address. I'd like you to go to parameter variation experiment, and I'd like you to go down, ladies and gentlemen, to the randomness area, and here we're going to set it to random seed. Mark my words. For parameter variation experiment, we will go down to randomness and set it to random seed. In fact, the very very motivation for this is that we want to be able to run this and test the effects of stochastics. So we need to set it to be based on a random seed. And then we're going to go down to this area called Java Actions. And this is where it may start to be a bit scary, but I want you to run through it. Now, ladies and gentlemen, the first thing we're going to do here for the experiment setup is we are going to set the fractional prevalence histogram 2D data. We're going to reset it so that it's empty, just like we did with the histogram. Remember that? Not long ago, we reset a histogram. Do people remember that? Before we put anything on it, we reset it. Before that for loop, we zeroed it out. Okay? Okay. Now, next thing is going to take a little bit of explanation. Ladies and gentlemen, this is a parameter variation experiment. The way it's going to work is it's going to run main several times over. In fact, we're going to specify how many times to run. Let's go see. So if we go scroll up here in the properties, you notice that there's this area that says parameters. And here, we're going to set it to be freeform. We're not going to change the parameters for this one. That's going to be the next one we do. We're going to do that after this. But we're going to run it, this model, we're going to run it, ladies and gentlemen, 50 times, 50 times over. Why? Because each of those runs will be a bit fluky. On each of those runs, there'll be different results. And we want to be able to generalize over these results. So we're going to run this model 50 times over what's called a Monte Carlo ensemble. And for each of those 50 runs, we're going to be adding its data to this histogram 2D. But that means for each of those runs, it's going to start main, initialize it, run it. Main will be done. Main will be finished. It's going to read the data out, put it into this histogram, and then it's going to throw that main away, and it's going to go back and start running it again. And it's going to run it, get the data out of it, put it in this histogram, going to go back and restart main. In short, till this point, we have been running experiments where the time the experiment is alive is basically the time that main is alive. The experiment comes into existence, runs main, finishes, they're both done. End of story. Here, the experiment is going to far outlive main. Main is a transient thing. It's going to come into being, be run, finish, and yield up its results, and it will do it again and again and again, creating main, running it, finishing it, harvesting the results, creating main, running, finishing it, harvest the results, etc. Do you appreciate that? Why are we doing this? Because we want to see the differences in the results from main over those broad set of categories. We don't want to make our decisions based on a fluke from one run of the model. Rather, we want to understand the regularities associated with that run. There'll be statistical variations, but ladies and gentlemen, there'll be regularities as well. Okay? Okay. So, ladies and gentlemen, let's finish the work. It required that explanation. There's a bit of Java code that needs to go along with it. May I introduce you to that Java code? Okay. Let me tell you. Remember I said that it's gonna run main, start it running, and then it's gonna read the data out of main for the result. What data will it read out of main? It will read the data set of fractional prevalence. That's what it's gonna read out of main. And it's gonna put it here. Put it right there. Okay? It's gonna put it into there. And it turns out the way it calls main is a strange name. It's strange to those from outside of computer science. It sounds very strange, but it refers to main. Main actually doesn't need to be called main. It could be called global, or it could be called, my world, or something like that. The point is, it's at the top of the hierarchy. Main is the thing that oversees everything else. All the other agents live within main. And the way we call that is because it's kind of at the start of it, and everything else branches out from it like a tree. We call it the root. Okay, root, R-O-O-T. Okay, so you notice it actually tells you this. It says root top level agent. So this is what we'll do, ladies and gentlemen. We're going to go read out the data set that we had in main. Where is that data set? Wherein lies it? It's this data set, fractional prevalence data set. We're going to read it out of main, and we're going to put it into this 2D histogram. So watch 2D histogram data. So watch this. After the simulation run, after main has done its job, we're going to go get that data set, and we're going to put it into this one here. So this is what we do. This dot fractional prevalence histogram 2D data. And just like when we had a histogram, we added each person's value into the histogram. Do you remember that? Do you remember that when we had a histogram earlier? We added each person's value, and we're going to add in here the data set drawn from main. And it's going to be called fractional population data set. There it is. It lies before you. That is the worst of it, right there. It required that explanation. Let me draw the analogy. So here we're reading a whole data set from main, and we're adding it into this guy here, which is a 2D data set. This is a regular old 1D data set. It's just over time, the values. Here we're adding it into something that records over bins of time the number of runs that have fallen to a given level. Let me show the analogy. This is, as I argued before, this is very similar to what we did with that histogram earlier. So if we were to go look at person here, and actually go look at main, we updated the degree histogram. Remember that? We wrote that before our break, before ordering the pizza or the food of your choosing. We cleared that histogram, and we went through each person in the population and added into the histogram data the number of connections that they have. Remember that? It's directly comparable to what we're doing here. Here, we are resetting the histogram, just like we did in main to reset that histogram. And then we're reading out of main the data set that it's accumulated and putting it in ours. Are we okay with that? If we're okay, let's run it. Okay? Let's run it. Run the parameter variation experiment. Ladies and gentlemen, it was born to run. Okay? So let's run it. Here we are. Now, it's going to be running this one. The secret is it actually runs it a lot faster than if you showed it visually. So you notice it's running it, and actually it's running it here in parallel. But nothing has shown up yet, and we're going to go investigate that. But let's go look at this histogram data here. Okay? Let's go see what's going on here. And, we see all 50 of them lie down here. Okay, now that's mighty interesting. Interesting indeed. All 50 of the runs lead to 0 down here, and then nothing after. Okay, so we're going to have to figure out why this is. That wasn't my impression. Let's go here and take a look. Okay, so one hypothesis I have is that that there's something wrong with the mechanisms used. Another hypothesis is we do have it dying down within 4 days. I am going to change it to here a very short duration of immunity. We're going to change it to 25 years in this parameter variation experiment. You notice it stars it to indicate that there's a difference from the default value. I change it to 25 years. I'm going to run it. Let's see what happens here. I would argue if we have a short duration of immunity, the infection will stay present for longer. Here we go, ladies and gentlemen. So now it's running, and you notice it's taking longer to run here. Okay, so it's running it many times over in parallel. We're going to scroll down, and okay, we see it increasing it, but it seems to be dying out. Dying out, I say that because the number of runs there is very small. Okay, so we need to figure out why this is. What is going on? Because that's clearly at variance from what we saw earlier. Okay, so I have a couple ideas in mind about what may be going on. I'm going to put in a bit of debugging code. After simulation run, I'm going to actually print out the data set that it read. Okay, here we go. So we're going to actually have it print out that data set. Okay, so that we could see something about the data that it's read from the actual simulation experiment and see what that's. Okay, so we go, and here it's printing out successive data sets, and we can see that they are that they contain a lot of values that are certainly not that close to zero. They actually have substantial prevalences in them. So I'm trying to figure out why is it that we don't see that quite clearly in the 2D data set. It seems that the data we're reading out is adequate. I'm going to run one of these with a brief immunity manually and just make sure the data set is fine, that we didn't truncate it here, and we'll go see that. My recollection is we explicitly specified it. Okay, so it for something like a little bit over 1,000 times. I'm going to go see here, and yep, we see that there's this data set maintained from time 0, so there's no problems there. Okay, so that's good. So why is it when we are adding it into this 2D data set we're seeing it truncated? Okay, so let's go look. The fox has shown its tail, of course. When we change these values for this data, histogram 2D, we needed to change we changed the x-axis count of bins, but what we did not change was the range of them. This should have gone from 0 to 1,000, ladies and gentlemen, and the y-axis range should have been from 0 to 1. Okay, so in this parameter variation experiment, we should make the number of intervals from 0 to 1,000. Okay? Zero to 1,000, and the y-axis can just stay there. So we changed 250, we changed this, but we did not change this properly. Okay, ladies and gentlemen, this should now go from 0 to 1,000. It was 0 to 1, and should now be 0 to 1,000. Okay? Having made that change, let's go see what this update brings. So it's a kind of odd default, 0 to 1, but it doesn't know the range you're dealing with. Okay, so now it's running, and notice it in parallel over many runs of this. You'll notice that in my virtual machine in which I'm running this, I have 2 processors enabled, and so this is running. Each of these processors is running a version of this model, is running main and a data set. And we're going to be summarizing, I believe the number was 50. We told it to summarize up to. So, ladies and gentlemen, what you'll see here is rather interesting. What you'll see here is that for this case where we have a mean duration of immunity of 25, we see fairly well-defined swings early on that exhibit little variation amongst the different runs. By contrast, in this area, there's a fairly broad stochastic sort of range because the vagaries of the runs, sometimes it's high here, sometimes it's low here. But you'll see there's broad regularities here. There's sort of broad orderly character to it. It's not that it's totally variable on any given run. It's not that it's totally unpredictable. There is variability, but it's variability within a range. Again, what is this summarizing at a high level? I mentioned it before, but I'll emphasize it again. What we see here is the x-axis here is time. The y-axis is the prevalence of infection in the population at that time. This is a 2D histogram, and what that means is that there are bins along this x-axis into which values are grouped. And there are bins along this y-axis. And each little dot here each little region there is summarizing, gives a total of the number of times, a color indicating the number of times that runs at this time interval fell within this range interval, within this level of prevalence. So it's summarizing the number of times that for that time period, the actual fractional prevalence lay within a certain range. Another way to think about it that I find useful is if you slice this at a given time, what you will get out is a histogram over the fractional prevalence, okay? At a given time, you've got a histogram here that kind of goes up, peaks here, and goes down again. And if you were to look at it from the side, you could see such a histogram. Let's explore this some more, ladies and gentlemen. Let's explore it a bit more, this 2D histogram. It's summarizing the effects of variability, capturing the orderly character. I'd like to go up for that parameter variation experiment, and I'd like to change the mean duration of immunity back to its default value. Okay? Change it to 50. Now I'd like to run this again. Okay? How do you think this will affect things? Now we have a longer duration of immunity. How do you think it will affect things? Okay, ladies and gentlemen, what we see here has a certain interesting character. Ladies and gentlemen, what we see is variability in terms of the fractional prevalence across different runs, but it's not, in contrast to the last one, which exhibited quite a lot of sort of regularities. Here there are regularities, but they're more subtle in character. What we see is that essentially all runs come down here. They exhibit a marked sort of swing up at the beginning and swing down in terms of fractional prevalence. In short, there's an initial outbreak quickly after the start. Now after that, many of the runs exhibit a secondary outbreak. Yet another fraction smaller exhibits several swings, several successive outbreaks in succession. But a large number early on come down around time 50 and remain at almost no prevalence. In short, it dies out. Some go down here after this after this secondary swing, and then additional ones go several times over and then die out. Ladies and gentlemen, that's a matter of stochastics. Matter of stochastics. I've heard utterances in the system dynamics world made in a sort of in a characteristic curmudgeonly style there, that when it comes to complex systems, stochastics are irrelevant. They have no place to play of any significance. They're just variations around the mean. Ladies and gentlemen, I point to this as a challenge to that claim. One of diverse challenges that I think would categorize it as a fallacious statement. Here, ladies and gentlemen, what we see is a situation where stochastics actually do matter. We can have very different characters of results, but they're not without regularities. And in fact, if you were to look at this, it's probably invisible from the distance that disadvantages you. But I can see from the side here, there's actually, there are some runs where there's some trailing sort of occurrences of patterns even out to the very end of this run. But what we see is that a successively smaller fraction of runs exhibit this kind of variation as time goes on, because a larger fraction have been beset by extinction events associated with the pathogen. Ladies and gentlemen, I'd like to stop that run, and I'd like to copy the parameter variation experiment and paste it in once more. Okay? Parameter variation experiment and paste it in once again. Okay? I would like to say parameter variation, and we're going to say population size 400. Okay? Population size 400. Not 100, but 400. Ladies and gentlemen, that will require that we set the population size to 400 in this region here. And it will require to maintain a comparable density. Remember, people are connected together based on the number of connections they have based on how far they are from each other. And a thing that strongly shapes how far they are is the density, how finely spaced or clumped these people are. And we want to retain the same density, so we're just varying the population size and not with that varying how dense they are and therefore how many neighbors they have, because that too will affect this. We want to control for varying one thing at a time. That would be the population size. We're not going to vary the average number of connections they have. So we will double space width and we'll double space height. Okay? To 1,000 and 1,000. Ladies and gentlemen, 1,000 and 1,000. It stands before us. Okay? And now we will run this. Okay? And we'll observe the course. Ladies and gentlemen, we see that there's a certain threshold of population size where the infection is unlikely to yield extinction early on. There are some. The presence of this area here is indicative that at least one of the runs of the 13 or so that have gone on have exhibited extinction by this point. That's why it's colored, because there's at least one which is down here. But what you'll see is some broad regularities associated with the continued sort of oscillations even until time 1,000. Okay. Now time is short, and I want to get on to some additional items. I also would like to show you a fairly nice feature of AnyLogic. And you'll notice, by the way, that it no longer is coloring there. That's not a sign nothing on. It's just it's occurring at such a small frequency that it's not actually showing it anymore, because it's showing it's concentrating in these areas to show this sort of variability. You'll notice this of color there is something which has some limitations because there's only so many sort of distinction. A couple further things, ladies and gentlemen. You can choose here to show envelopes, which I trust, although the documentation is poor, around the median. Or you can show bins, which are actually the number of counts. And I had thought that we were displaying the bins before, but we were actually displaying envelopes around the median, I believe. I'm going to choose it, change it to show bins associated with this 2D histogram. And if we run this, ladies and gentlemen, what we will see is is a little bit different, because we're not merely showing empirical fractals or quantiles around a mean, where it's sort of number of cases where it's fallen in a single region. Okay, and this is going to lend itself to a graph that's a little bit different. It's not as centered on kind of the central tendency, the median. Rather, it is showing how commonly they fall within certain ranges. Okay, so ladies and gentlemen, variability. Variability is not merely neat fluctuations around the mean. It can lead to very divergent behavior, particularly with nonlinear models where you have lock-in effects. You may get very different paths undertaken. Eventually, with very little probability of falling between them, you can have two extremes, for example. One extreme of extinction, one extreme associated with presence of a pathogen, for example. So something of interest, okay? Okay, ladies and gentlemen, now we're going to turn our attention to, so what we've just seen is a example motivating examination of the results under stochastics. And we could run it for longer, we could run it with different parameters, but I really want to, before lunch, I would like to show you how you can use these same parameter variation experiments to probe the behavior of the system as we change parameter values. Okay? So I would like to go here, ladies and gentlemen, and take a copy of parameter variation. Probably I should call this parameter variation baseline. Okay? Parameter variation baseline, just so we know it's a reference with default values. We're going to copy that, and we are going to paste it into the model here as a whole. So we're going to have a parameter variation baseline 1, and here we're going to call this parameter variation sensitivity. Okay, and we could name it for a certain type of sensitivity, but we're going to vary this a bit. Okay, parameter variation sensitivity. So we're going to be altering the values of parameters. So ladies and gentlemen, in this parameters area, instead of doing freeform with a fixed number of runs, we're going to systematically vary the parameters within a certain range. Now we could do this on a one-way basis or a multi-way basis. I should note that the freeform style can be used to perform Monte Carlo ensembles here. So you could draw this. So you don't do this right now, but we could draw this, for example, from a uniform distribution between one thing or another, 5 and 15, for example, 5.0, 15.0. We could do that. We could draw them from a normal distribution, a truncated normal. We could draw them from a beta distribution. We could perform Monte Carlo sensitivity analysis by drawing the parameters, sampling the parameters from distributions and running the model accordingly. To be clear there, the model, at any one time, the model will be run with a particular value, but each time you run the model, the values will be drawn anew from some distributions. Here, we're instead going to vary the parameters within a range, okay? So I am going to, for example, vary the mean duration of immunity from 25, okay, so here we should change this from fixed to range. We're going to vary it from 25 days up through 75 days with a step of 5. In other words, it's going to simulate it for a duration of 25 of immunity, 30, 35, 40, etc. Okay? Now, if you wanted to explore it logarithmically, what you'd do is you'd create a parameter. So you want it to be multiplicatively growing. You could create a parameter as the log of the parameter you want to take and expand that to go up by fixed size, and then take the exponent of it to have it go up in some sort of multiplicative way. The log of it would go up additively. The exponent of it would go up would go up multiplicatively. So let's try this. So here we are going to run the model a bunch of times. Now, you notice we can't specify here the number of runs because that's implied by these ranges and step sizes. It's implied by the design here. So now it's running it, and you'll notice that it ran 11. Why 11? 25, 30, 35, 40, 45, 50. You can count them up, 75, to reach 75. It includes both 25 and 75. And you'll notice here that a large number of the runs, it seemed to die out very quickly. Okay? Why do I say that? Because this is very bright compared to, I don't know if you folks can see it, but there's kind of a fringe here where there's a smaller number of runs early on, particularly. By earlier on, I mean at smaller values of this, where it exhibited variation. So we could go in and say, okay, let's examine it here from 25 to 50. Right? Let's do it in that range. Let's go by that, and let's examine the variability there. So here we go, and so we're running it, and here's 25, 30, etc. And it ran 6 runs. Okay, we have the option here of doing it more finely. Instead of doing it with a step of 5, let's do it with a step of 2. Okay, step of 2. Could be 2.5. Okay, let's try this. I did it as 2, and let's run this. And instead of getting 9, we're going to get 18 different simulations. You know, it's putting on here, and we can see that for the first bunch, they exhibit this kind of behavior where it's endemic, and then for later ones, there's kind of perhaps a second spurt, and it rises. Okay, so that's interesting, but you could say, well, wait a minute. You were saying before it's not that reliable to consider only running it once for a given set of parameters. Maybe we want to understand stochastics within each of those. Fair enough, there is an option for doing that. If you scroll down, there's this thing called replications. And replications are going to allow you to, if you wish to do so, should you choose to do so, to run it several times for each of those variations and parameters. So the idea here is that this model is going to be dependent on the parameter values for sure in terms of broad regularities. But there's some stochastics around that. We know that from those earlier graphs. Even with a fixed set of parameters, it's going to exhibit some variability, particularly in the later stages. So we could, for each of the possible variations of those parameters, each of the specific assumptions of the parameters, use replications and run it, let's say, let's change it to 5 times for each of those. Okay? 5 times. And incidentally, there's an opportunity to allow it to kind of reason out how many replications you need for statistical reliability. I've gone into that. You'll find me explaining slides in online presentations on stochastic, on either parameter variation or I think more likely context. Okay, so here we are. Each is now 5 times, and we'll go on to another set of parameters. Okay, here's another set of parameter values 5 times, and so on and so forth. Okay, so here we're taking into account both stochastics on the one hand and variations in parameter values. Okay, so here we've got some variability going on, and once again it's kind of heavy on the lower side. Okay. Now, one could also say, well, wait a minute, you've only varied one parameter. Could we vary another? Sure, change this back to fixed. And we could vary for example, infectious duration. So suppose we were to have infectious duration go from 5 to 15 with step 2, right? Say step 1, 5 from 15 to step 1. It starts as small as 5, goes up to 15, and that's a step of 1. Kurt, has it arrived?
No, wait for me to pick it up.
Okay. Oh, okay, yeah.
Or no.
Thanks. Appreciate it. Okay. Okay. Okay, ladies and gentlemen. So the infection duration from 5 up to 15, and for each of those we're running at no fewer than 10 times. You can already see a bit of a fringe here, although we're only through 2 of those values, I believe, at the time I was speaking. Here it's increasingly filling in. For the later values, as infection duration creeps up, we get more and more cases where the infection remains endemic. It survives for a long time. Okay, and I need to switch back to it. Here we go. And it's running along, and you'll see quite a bit of variability here. Okay, parameter variation. But that's one-way parameter variation. We could examine multi-way if we wanted to. We could say, okay, let's also have, for example, mean duration of infection vary from 25 to 50 with step 5 at the same time as we're varying mean infectious duration. Okay. Now that would set up a sort of grid of sorts where all possible values for mean infectious duration would be crossed with all possible values of mean duration, and we could run that. For speed here, I'm going to turn off the replications. We've seen them, how they could be used. I'm going to turn them off here because I have additional thing I'd like to do before the pizza arrives. So I turned off replications, but I'm doing this multi-way. It can be done with replications, don't get me wrong. It's just that I for speed. And we're varying both parameters at one time. It's crossing all of them. Now, you could reasonably ask, that's okay, but how if I want to design my own experiment? Suppose I don't want to do it evenly. Suppose I want to sample more in certain regions. Those things are readily doable. One thing you can do is index a parameter along, and you can read the values to use for the other parameters, for example, from a spreadsheet. Or you could read it from a table function maintained in AnyLogic. It's not a problem if you want to do them. It's just that there's no super nice interface for specifying your particular Latin hypercube sampling strategy for getting exact, at least one value of each parameter being guaranteed to occur at least once, or at least once where it falls into a bin or what have you. But these things can be readily done with a little bit of mechanism if desired. And there are tools which can be used to generate Latin hypercube samples, which have certain properties that they guarantee in terms of sampling. Of which you may wish to avail yourself, and you could put it in a spreadsheet or database and read it in here. Okay, so ladies and gentlemen, parameter variation sensitivity here. I hit 2 things, and I hit them two broad themes on that particular topic. One of them was you have running a model many times so that we draw conclusions that are robust under the stochastics, that aren't merely the result of a fluky run. And we saw how that could be accomplished very readily by just using fixed values and running at a certain number of times around, say, a baseline, around some alternatives. Because remember, the results may be more variable for certain values of parameters. Alternatively, we also use parameter variation experiments to vary parameter values. And I argued that this could be done in fixed ways, fixed additive ways, kind of like this, where we vary one parameter or several. Or we could do it by drawing from Monte Carlo ensembles for the parameters, where we sample from distributions associated with each parameter. Okay, and there we could examine, given those distributions on the inputs, what do the distributions on the outputs look like? What sort of distributions do we see over the outputs? We also noted the presence of the capacity to use replications to explore the the stochastics when we're varying parameters to examine, okay, for a given assumption about parameters, within that variation of parameter values, we want to capture variability. That's that extra layer of stochastics that we could capture the different realizations via this use replications component. Okay? We saw how we could use this construct of a 2D histogram to summarize data and its corresponding 2D data object to summarize data across runs. We saw that it could allow us to summarize it as sort of empirical fractiles or quantiles versus as bins. And we saw that we could here specify, amongst other things, envelopes, but we could specify sort of ranges to use, binning, preferences, etc. Powerful set of mechanisms. Powerful set of mechanisms. Any questions before I cover one final thing before lunch?
Yes, question about
Yeah.
the plots. So you don't know what parameters are being shown.
Yeah, yeah. Fair enough. Okay.
You get the variability, but you don't know.
Correct. It's a fair comment. Yeah, I think that's a good point, because you're putting them all into a kind of a set of buckets which don't record. You know, it's counting for bins. It's counting the number of times it fell within a certain area, and you're not keeping track of when did it count. I mean, so I think that's true. And one thing you could do is produce different versions of that graph for different ranges of parameter values. So, you could, instead of having it go from 25 to 75, you could have it go from 25 to 30, see where they fall in the range, 30 to 35, etc. I will show you here, not directly responsive, maybe I'll do it around the baseline one rather than around this one. I will show you that that when you run this, there is the capacity to more further output data that you may us. And I run it here. We're running it along. Oops, I paused it. Running it along, and here we ran it. This is for the baseline, and here, if we right-click on this, you'll notice it says Copy All. Now, if we go over to Excel, and we were to go produce it in a sheet, for example, what you can get here is the underlying data from that binning. So this indicates different bins. You'll notice that in specifying this, I indicated, for example, that this x-axis is extending from 0 to 1,000 with 250 intervals. That implies each is of length 4. So hence the first bin in the time dimension is 0 to 4, the next 4 to 8, the next 8 to 12. Now, in the y-axis there, I had requested 100 from 0 to 1, hence each of them is of size 0.01. And that's what it summarized. And you can actually see the curves here, kind of, if you look at these values. Probably what would be nicest is if I went like this, and I did conditional formatting, and I did color scales, and did something like this, where you can see kind of from the coloration alone, you can see some of the values. This can be exported to R or SAS or what have you, so that you could conduct further analyses. That isn't addressing your point, but it is something which provides opportunities for additional analysis. Really, to address your point, where I would probably turn would be this issue of subdividing the space into different regions, and then I could see for this region of parameter values, it exhibited this patterns of variability. For this other one. It can be cumbersome, but it's a lot better than doing it purely by hand. Other questions? Scott, yeah.
I just had a couple of comments. One, you can directly output the output of the runs after every run, so it's not like you can't get that along with the input values. Generally, with multi-run experiments, you have to be careful where you're writing it so you don't overwrite them. But then I also wanted to say something about the comment Dr. Osgood made earlier about the variability and particularly how system dynamics use stochastics as something they can simply waive. And this is, frankly, something that they teach in system dynamics. I've seen it every single system dynamics textbook I've looked at. And it happens in agent-based modeling that stochastics become important, generally because you're exogenizing variables. You're just randomly selecting things. Discrete event simulation, on the other hand, is grounded in queuing theory, and one of the most basic elements of queuing theory completely invalidates the system dynamics approach to stochastics, which is something you simply abstract over. So if you have an arrival rate into a process, a queuing process of lambda, and you have a service rate of mu, then the utilization of a single server of that queue is lambda over mu, long term. Now, what's interesting is that if these two are equal to each other, and there is no variability whatsoever in things, so I have exactly someone arriving, one person a minute, and it takes exactly 1 minute to serve them, then the average queue after an arbitrary length of time, infinite amount of time, is 0. If there is the slightest variability around those numbers, then the average number of people in the queue after a certain amount of time is infinity. This isn't just, oh, we can abstract over it. You can't, okay? Queuing theory is a theory that is highly stochastic by nature, and so you simply cannot get rid of stochastics no matter what level you abstract it to, all right? And that's crucial for how discrete simulation works, because it's basically the simulation of queuing systems. And this is one of the biggest issues with getting at least the practitioners of different modeling methods to talk to each other, is how they view stochastics. To me, when you say, oh, I don't have to worry about stochastics in a model, as a discrete event simulation person, I'd say you're not modeling anything at that point. You're just, oh, it's pretty. You know, system dynamicists are like, well, you need to get high enough, and we even saw that. When you get higher and higher populations here, the stochastics start mattering less and less. Okay, and so there is some argument here, but there are some disciplines, such as queuing theory, where you simply cannot get rid of stochastics and be sufficiently going. Just wanted to say that real quick. So.
Yeah, I mean, in system dynamics, the attention is on capturing the endogenous dynamic characteristic of the system, and it tends to lead to models with rather different scopes associated with them. And as a result, the nature of the effects that they're interested in investigating tend to be somewhat less affected by stochastics, although I would argue in many cases very dependent on them. So I really want to get to some additional material, though, before the pizza arrives. Just to mention to Scott's point, although it isn't a matter of summarizing things, after each simulation run, you could output the data set that comes out of it. If you wanted to put it into an Excel file, you wanted to put it into a database, there's certainly no problems doing that. It just isn't summarizing that. Okay, but let's quickly get to this final point, which is not so much in the area of it's a parameter variation experiment, but it's an additional mechanism. And it has to do with input-output. And this is another common need. Ladies and gentlemen, we have summarized incident case counts yesterday. We saw we needed a variable to do that, to summarize the number of people who over the course of a week got ill. By contrast, the statistics will summarize at a given time the state of the model, and can do admirably so. But if we want to look at statistics associated with what I would call flow statistics, but things that are changing over time, AnyLogic's built-in statistics, as manifested through the population, are not going to be responsive to that, not directly. And you're going to need to start putting in additional mechanisms. I want to, we also saw how we could add a histogram, for example, for other characteristics, again, cross-sectional. At the current time, how many people have a certain number of connections. What I'd like to do now is to show you longitudinal data at the part of an individual So not just longitudinal data over the course of a week, how many people got infected, but at the level of an individual. So I'd like you to go to palette, and I'd like you to go to person here. Does anyone want me to upload my model, by the way, right now? Is it high urgency? Okay, I'll do it in just a few minutes. Okay, I'll do it, yeah, in just a few minutes. Okay, so if you go to person, ladies and gentlemen, okay, you go to person, I'd like to add into person from the palette, and you can do it from the agent palette. I'd like to add in a variable. And this is going to be count times infected. Okay? Now, that's a count. What do you think, what sort of type do you think it'll be? Sorry? An integer indeed. And its value will start at 0. So its initial value is 0. Okay? Now, where would we increment that value? If we want to keep track of the number of times they've been infected, where would we increment it? Where could we implement? Give me a good place. Yeah, when they enter the infective is as good one as any. We could alternatively have it at that transition. Let's do it in the entry. So how would I increase it by 1? This dot count times infected plus plus. That means increase it by 1. Take its value and increase it by, make it 1 bigger than it was. We could have written it as count times infected equals count times infected plus 1, but that's more wordy and it kind of requires us to be clear to look at both sides to make sure it's the same variable, read closely. Just crisper to put it this way, and I hope you don't mind me forcing exposure to that. Great. So now we're keeping track of longitudinal data on an individual. This is something of import, ladies and gentlemen. To have a model which can track person's history over time, not to be assumed. An aggregate model gives, aggregate system dynamics model gives cross-sectional views. It's not going to be able to track details of a person's history. At any one time, it will summarize how many people have a certain characteristic, but it's not going to be able to track their history. Now we can. So let's go do something with that. Ladies and gentlemen, let's go to projects. And let's go to main. Let's go down main. And I'm going to ask you to win one for the Gipper, okay, before lunch here. What we're going to do is the following. To expedite the process, we're going to copy these 2 histograms. Let's add in a new histogram just so it's easier. It's not going to save us that much time. Okay, let's go to palette. We're going to add in 2 components. One is going to be a histogram. Here we're in more familiar territory. We're going to add in a histogram from the analysis plot. So this is going to be a histogram. Okay? And what do we add if we're going to add a histogram? What else do we need to add typically? Histogram data object. So we're going to go add a histogram data object as well. And this is going to be called infection count histogram data. And correspondingly, the infection histogram will be called infection count histogram. Are we okay with that? Okay. Now, the infection count histogram is going to be set to not update data automatically for the data update. Are we okay with that? Yeah? So, in other words, and what am I doing? This should be, oh my gosh. I should have called this infection count histogram data, this data object, and then called the other infection count histogram. And instead, I was confused, and I confused the names. Okay. So, infection count histogram and infection count histogram data. We want to set infection count histogram data to not update automatically. And, ladies and gentlemen, we're going to leave its value blank. We're going to fill that in that very event that we added earlier. Next, for the infection count histogram, what do we need to do to kind of wire it up to use the data object? Anyone remember? add histogram data. So this is going to refer now to the infection. So this is going to be infection count is going to be the title, and the histogram, the so-called histogram associated with it, is going to be this dot infection count histogram data. Okay? Great. And ladies and gentlemen, the data update will be do not data update data automatically. Okay? Okay. Now we're actually most of the way done, ladies and gentlemen, but I need you to add one more thing here. Okay? I need you to add in a plot. Okay? Not a time plot, a plot, a scatter plot, in fact, it will be. And this will be called, in fact, it'll be called degree infection count scatter plot. Okay? And in terms of data update, it'll be do not update data automatically. Are we okay with that? We're getting very close to being done. We okay? Ladies and gentlemen. Ladies and gentlemen. Next, I am going to go to that event we added earlier called update degree histogram. And ladies and gentlemen, we're going to change that to instead be it'll be called update histograms, or update plots it will be called. How's that? Okay. Okay. Update plots. Okay. Great. And we're going to for this change its name to update plots, and we're just going to put a little bit more code, and then people will be free to eat here because the food is being unpacked, I think, as we speak. Okay, update plots. Okay, we're going to keep what we have there, but we're going to add some things to it. First, we're going to update both of these, we're going to update these plots above. So we're going to have infection count histogram data. So this dot infection count histogram data dot reset. We want to reset that histogram as well. Semicolon at the end. So that's at the beginning. And then we are going to go and, okay, so this is what I wanted, right? Okay, great. And if memory serves me, this dot, forgive me for just a second, degree, I'm just trying to remember if this also requires, no, it's degree, it's this other one, degree count scatter plot dot, do we have to reset? No, okay. Okay, and we're going to say degree infection count scatter plot dot remove all. That's going to remove all the dots in that scatter plot. Are we okay with that? So, just as a reminder, these are the two things we just added. An infection count histogram on the one hand, and then a scatter plot on the other. Okay? We're going to remove the items in those. Okay? And now all that remains is to fill them in with the data from each person. So ladies and gentlemen, here we need to have several items in this loop. Does anyone remember in Java, if we want the loop to go over not just one line, but several lines. Not just one statement, but several statements. Not just one command, but several commands. How do we do that? We put brackets, curly brackets, ladies and gentlemen. Okay? Okay. Curly brackets. Okay? So after the existing line there, but inside the curly brackets, this will kind of let it treat all of this as one line. I would like to write this dot infection count histogram data dot add, and we're going to add, what do you think? What do you think we're going to add in to the infection count histogram? Persons what? Yeah, that count variable. Count times infected. Remember that? We just added it. That counts the number of times they've been infected. Do you remember that? Next. Is the food ready? Great. Next. This dot degree infection count scatter plot dot add. Okay. Mumble. Okay. Okay. I know what I. Okay. Oh man. Okay. No worries. We'll get that fixed up in a jiffy. Okay. Okay, ladies and gentlemen, I did a boo-boo. I didn't remember in my head. Infection count scatter plot. They need to be associated with data, and what you associate with is a data set. A data set, ladies and gentlemen, here, and we're going to call it. So I went back up to the degree infection count. This is going to be called degree infection count data set. So I just dragged the data set in. Now this data set is going to be different from all other data sets that we have frogged, because it's not going to use time as an x value, a horizontal value. Okay? It's not going to. So we just drag this in, this data set. We uncheck use time, and we're going to indeed have it do not update data automatically. However, there's one final thing we have to do. If this goes with this scatter plot, what does the scatter plot need to do? Do you think? Well, it needs to know about it. It needs to refer to it. So under the data here, we're going to point it to the data set. In this data set, ladies and gentlemen, will be, so the data set, the title will be degree versus infection count, and the data set will be this dot degree infection count data set. Okay, and here we go, degree infection count data set. Okay, and it is, and now down, so having done that, having wired up that data, that scatter plot to refer to the accompanying data set, this new data set that we had, and making sure the new data set had unchecked this box. Oh, and we wanted to keep up to 10,000 latest samples for this data set. We now want to go, for this data set, up to 10,000, we now go down and finish our code and update plots. Ladies and gentlemen, we want, instead of saying degree infection count scatter plot to remove all, we want degree infection count data set dot reset. Degree infection count data set dot reset. And finally, we're going to have, in the last line of the loop, degree infection count data set dot add, and it's going to have two things. What's the first thing going to be? Their degree. How do we get that? Yeah, person dot get connections number. What's the second thing that it needs? The count times infected. Person dot count times infected. And there you have it, ladies and gentlemen. I'll put it up on the big screen for all to view. Okay. Now it's a happy camper on mine. So soon, I hope it'll be a happy camper on yours. And you will be able to go to lunch with an empty stomach, but a full, content mind. Okay? Okay, so ladies and gentlemen, these first three things, those serve to reset the data sets associated with this. This loop then loops over things. And the way it's formatted here is adverse. It exhibits aesthetic distress. What this was supposed to be is this. Okay, so the idea is here we're adding in the connections number to the degree histogram. We're adding into count times infected to the infection count histogram, and then to this final one we're adding in a pair, the get connections number, which is the degree, and the count times infected. And that's because this is a degree infection count scatter plot. It's a scatter plot of that. Does that make sense? Can we run it now? Yeah.
Oh, I'm just curious. There's no parenthesis, like pair at the end of person.count times infected. There's just
There isn't, because that's just a variable within them. By contrast, it's a good question. This is just a variable. And you'll notice up here as well, it's just a variable. We need this begin paren, end paren when we're calling something. This is actually a function in person that says, get me your number of connections. By contrast, this is a variable we introduced. This is a function provided by AnyLogic. This is a variable we introduced.
Thank you.
Okay,
Yeah.
sure. Okay, who needs TA help? Okay, so you should be able to run this then. Run the baseline, and we should be able to see these graphs evolve as it runs. I will scroll mine so that you can see them evolve up here. Okay. Here we. Oh, you know what? We should have set the. We should have set the. Should have set it so that we didn't have these lines connected. Okay, what I will do is go up to that plot, this plot up here, degree versus infection count, and we want it in terms of appearance to not draw the line. Okay, not draw the line. And now, because of the vagaries associated with the baseline, I'd like you to simulate it for the case of population 1600, okay? And we should be able to see it. So how did I do that? I went up to this plot, and I went down to appearance. I had to expand it, and I set it to not draw the line, okay? Not draw a line. Okay, now, I'm going to go down to population 1600. And here we go. Okay. There we go. It's and the plot of infection count. Everyone right now is no infection count. Okay, everyone right now, regardless of degree, they have they've only one time infected. Now it's going down, and you'll notice it's going down, but we're having a second swing up. So here, some people have been infected twice now, some fewer. And you can see here, most people have been infected twice, okay, some 2 times, some 3 times. And here we have this kind of variability as things are going up. And as a general rule, what you'll see is those who have connections, there's a somewhat of a trend here that the more connections that you have, you'll tend to be infected more times. Okay, here we are, and as this goes up, you'll see more of that trend. This provides a number of times people have been infected. This provides a scatter plot showing how their degree infection count on the other. And you can see there's limited variability in this population. but as a general trend, the more connects you have, it tends to be that you have more times infected as a result. Okay, so there's somewhat of a tendency this way. You notice here the population is being infected more times historically. This is the prevalence. Here's the number of connections that people have. And I was planning to do it, but I would leave it as a little exercise to ask, okay, if we went to Maine, and instead of imposing a distance-based network, if we instead impose a scale-free network with an M of 5, how would that affect things? How would it affect the dynamic scene? And once again, I will just run this, and we'll just break for lunch here. Okay. So I'm running it with that scale-free network with an F5 here, and in this network, some people have lots and lots of connections. Those are the big ones, and then some people have fewer. Most people have fewer connections. You could see a very wide swing, and you'll notice that this graph is very different in terms of the distribution of degrees. Before, most people were clustered around 10. Here, the average may be 10, but you have some people with 100 connections. And up here, you have a pronounced variability, a marked variability in terms of infection count. You know, as we play this forward, what we'll see is the people who have large numbers of connections tend to be sort of magnets for infections, and they tend to spread it to more people. Okay, so here you see variability. If we had more time, I would create separate graphs for the number of times people have gotten infected for those who have high degree or low degree, or the distribution over degree for those who have been infected more than a certain number of times. But here's a little scatter plot. Each of these points is a person with a certain number of a certain degree of times infected on the y-axis. And once again, you can see those with small degree tend to have somewhat lower burden of infection than those with high degree. If you have low degree, you could have gotten infected a lot of times, but in many cases it's smaller. If you have a high degree, you're almost certain to have been infected many times. And that, ladies and gentlemen, illustrates a sort of statistical property that's emergent from this model. This kind of curvilinear relationship between, on the one side, degree, and on the other side, infection count. Okay? That's all for this morning. Thank you for your patience holding out to lunch. And as I say, you now go to lunch with an empty stomach, but a satisfied and full mind. Thanks very much.
Can I just give a couple instructions for them?
Sure.